Hello everyone, welcome to Introduction to Machine Learning for Data Science Beginners course. We are going to learn first what is machine learning and what are the types of machine learning. Machine learning evolved from a computer science that primarily studies the design of algorithms that can learn from experience. To learn, they need data that has a certain attributes based on which the algorithm try to find out some meaningful predictive patterns from the input data. And then finally, it generates a target output. The classification of machine learning is generally a four type. They are supervised machine learning, unsupervised learning, reinforcement learning, and semi-supervised learning. In a supervised learning, we have input data and output label or a target label. In a supervised learning, we do not have an output or a target label, we have only input data. In reinforcement learning is a kind of learning which is a continuous learning in a real environment. In a semi-supervised learning, we have a kind of output data and as well as input data for the prediction. Categorization on the basis of required output, we can classify machine learning algorithms in three types: classification, regression, and clustering. In classification, we have a certain type of output or a finite number of outputs. In regression, we have a continuous type of the outputs. And in the clustering, we do not have any special type of the output. I mean to say, in the clustering, in general, it produces the finite amount of target output, but we do not know how many output it is going to produce in the clustering. But in the classification, we know before training the algorithm that there are a finite number of classes in the output, but in the clustering, we get after the training our algorithm. And this clustering is unsupervised learning. There are many tools available for machine learning algorithms like Scikit-Learn, TensorFlow, Keras, K-Train, and the PyTorch. So we'll be using kind of all of these libraries or Python packages in our course, and we will be utilizing these things very beautifully in this course. These are some of the famous algorithms, although there are many more type of the algorithms, but in general, these are the famous algorithms for the beginners to get started with the machine learning. I have another course on advanced machine learning, and that is specialized in advanced NLP course, and there I have described a little advanced algorithms in machine learning, and I have also described how you can deploy your machine learning algorithms on the internet. You can go to my profile and then you can enroll in that course. The basic type of the algorithms are regression, logistic regression, SVM, decision tree, and the random forest. A regression is a regression type of the algorithm where we have a continuous type of the output. A logistic regression, SVM, decision tree, and the random forest, although these can be also used as a regressor. So mostly we will be learning about these four type of the algorithms at the first, and then we will be also learning CNN, RNN, and LSTM GRU transformer later in this course. There are many type of the clustering algorithms such as the k-mean clustering, k-shift clustering, density-based spatial clustering of applications with the noise, expectation maximizations clustering using Gaussian mixture models. So these algorithms we will be also discussing later part of this course. These are the model training, and this is the schema how in general we train our model. Let's say we do not have a data, so first of all we need to collect the data, thereafter we clean the data, alright, and then we build our model, thereafter we train it and then we validate it, and then we test it. If there is any error, then again we train it, validate it, and test it. Once model is finalized, and suppose that at this place you have got your final trained model, then at the stage of the deployment, Then we can also do directly feed this data which is coming from data cleaning directly into the model testing, and then we can again test our model. Alright, and thereafter once this testing is done, then we can deploy our model. And if you see it at the abstract level and at the stage of the deployment, it is kind of, let's say you have here level data and training code. So this is kind of the data which you want to train. Then you build the model. Once model is built, then you write an application code for your model deployment which runs at the server. Thereafter, once it is deployed in the production, then you call this model prediction using HTTPS request, API requests, and then finally you receive the data or predicted data. Alright, so during the training, we actually divide our data in two sets. It's a training set and test set. Sometimes we also divide this data in three sets: training set, validation set, and test set, as we have already seen it in a previous slide. So the training set is a subset of the data which we use to train the model, and test set is the subset of whole data which we use to test the model. And similarly, if we talk about the validation, we can say that the validation is a set of the data or a subset of the data which we in general use to validate our model. Alright, perfect. So the one more thing you need to pay attention here is that, let's say once you have splitted your data in training set and test set, you should also make sure that your test set meets the following two conditions. Your test set should be large enough to yield statistically meaningful results. Alright, that mean it's like that. It's not like that. I split your data in just 2 or 3 instances of the testing set. Split your data in at least 10 to 20% of the data so that you can actually test your data in a larger variety, of your data. Then the second step is representative of the data set as a whole. That's mean whenever you get this test set, alright, so in this test set, you should have all the type of the data as most as you can try. It means that, let's say, if you have the two classes, class 1 and the class 0, and if you put all the data of class 1 in the test set, then you are not going to good accuracy. In fact, even though if you get the good accuracy, but that doesn't mean that your model is robust, because you have just placed a single type of the labeled data in the test set. So you should try to put a balanced type of, that's mean it should include all the type of the data in the test set. In other words, you can say here, don't pick a test set with different characteristics than the training set. Alright, perfect. So this is all about in this lesson. Thanks a lot for watching it. I'll see you next lesson. Hi everyone. Welcome to Linear Regression and Data Analysis on a Boston Housing dataset. We will be doing here house price prediction on a Boston Housing dataset. But before we get started with house price prediction, we need to understand what is linear regression and what are the use cases of linear regression, and thereafter we will learn how we can build a model for a linear regression. So let's suppose that you are a real estate agent and you want to predict the house price. But you may ask a question that why you want to predict a house price? Because you are a real estate agent, many customer and client coming to you, and you want to sell a lot of house. But you always want to, whenever you need to sell a house, but before that you need to also buy a house. And for your own purpose, when you buy a house, you have to know that what will be the estimated cost of that particular house in that particular area. So what you can do, you can collect a data set around that city of the house prices, and thereafter you can write a linear regression algorithm to predict the house price, or you can say that the house price of any house in that area. So in the same way it works, and you want to make it there an automated system which can actually predict the house based on the various input such as house locality, what is the area of that house, and there is how many number of rooms in that house, how far it is from city, how far it is from highway, and how far it is from river. All those things you can take as an input feature. Thereafter you can identify that what will be the expected price of that particular house. So in this regard, we will be using here a supervised machine learning algorithm. There are two types of machine learning algorithm: supervised machine learning algorithm and unsupervised machine learning algorithm. So linear regression is a part of actually supervised machine learning algorithm. All right. So you may also ask a question, where can linear regression be used? Linear regression is something like that. There is independent variable and you want to predict their dependent variable. So this y is dependent variable which can be seen as house price, and x is independent variable which can be seen as number of room in a house, number of bathroom, or you can say the total square feet or square meter area of that particular house. So this one is independent, and these dots are actually actual price of a house, and this red line can be seen as a regression line, or you can say a fitted line. The linear regression is very powerful techniques and it can be used in various cases, such as you can also predict, or you can say that you can forecast a sale in coming months or in coming years. You can also gain insights about the customer behaviors. You can understand the Twitter popularity. You can understand the stock prices, etc. So we'll be discussing these things in the coming lecture. So this is all about in this lesson. Thanks a lot for watching it. Alright, now let's go ahead and try to understand what is linear regression and how we can make its model. Moreover, we need to understand how linear regression model works. First of all, as you know that regression is very important machine learning model where you want to predict a target variable as a continuous variable. Do remember, classification, in a classification you do a classification where a target variable are categorical variable. That means the target variable have only some limited values like 1, 2, 3 only, like the classes, it's like a human, bird, animal, etc. But in the linear regression you have a continuous output. So there you have to predict some number in the output. So there we use a linear regression. The linear regression works something like this. There you have data which is treated as input data, which you can also say that the input feature, and the total number of columns present in the input is known as total dimension of a feature. Dimension of feature means how many column or how many unique number of features present in the data. Do remember, it's a unique. If there is duplicate features, then you need to remove those duplicated features. Then you have this data. Thereafter you can do the pre-processing on the data, like the data cleaning, like the duplicate removal, and if there is null values, then you can impute those null values. So this data pre-processing you can do. Thereafter you have to feed this data into a regression. So this regression learns a relationship between the y and x. So there y, as I have already told you that this y is the target variable and x is the input which is independent variable. So this regression model learns the relationship between the independent variable and dependent variable. Once this regression model learns the relationship between x and y, then it is able to make here intelligent decision. So in intelligent decision, It can predict your house price, it can predict stock price, it can predict the Twitter popularity. So these things it can predict. Do remember one more thing, the Y prediction will be always continuous. A continuous variable means you have a number which have infinite resolution, like a number 1, 2, 3, but in classification you have a fixed number of labels. But in regression you can achieve infinite resolution, like 1, 2, 3, 1.1, 1.2, or 1.11, 1.101, means you can predict any value in a number range. All right, perfect. So this is all about in this lesson. In the next lesson, I'll show you what are the use cases of regression. All right, now let's go ahead and try to understand what is the regression example. Regression can be used in a stock price prediction as well. There we predict the stock price of a particular company's stock. There you have a dependent variable which is X, and in the form of X you can take many input variable, like you can take the recent history of a stock price, news events, and thereafter you can also take the recent history of opening and the closing stock prices of the competitor, and any political decisions are made in those area, and these things you can take into account. And thereafter you can also take the history cases of the competitor. Those things you can find as a dependent variable. Thereafter finally you can predict the target variable, which is a stock price of a particular company. Do remember, in case of stock price prediction, only a company's data is not sufficient. You need to also get the data of a related companies. Like, let's say if you want to predict the here the stock price of Google, then you have to also know the stock price of the other related companies, top 10 companies like Facebook, Apple, Amazon, and Tesla, etc. Why these things are important? Because when you want to predict the Google price, the Google is actually, the dependent. It's not the dependent, but overall the stock price goes in the same direction as other companies' stock price goes in which direction. So the moreover, if you include the data of other companies as well, then you will be able to get the better stock price prediction. But in the last, you have to actually include only the related companies. For example, if you want to predict the stock price of the Tesla, then you can take those companies which are making rocket, which are making automatic vehicle. So, and all those companies you can take, and then finally you can predict the stock price of the Tesla. Although the Tesla doesn't make rocket, that is the SpaceX, but still, since this is Elon Musk company, so you may include these companies. So the another example is tweet popularity. You can also use the regression model in tweet popularity. You can estimate the number of people who will retweet a particular tweet based on the input feature. The input feature could be like what is the sentiment of that tweet, for which you want to calculate the how many number of people is going to retweet that tweet. You can take the input feature, how many followers of the person who has retweeted, and how many followers of the person who has actually tweeted this, and how popular hashtag is there, the tweet which has been included there. Thereafter you can also take the other input features, like if it is male, female, and if it is celebrity or not, if it is related to any political party, and if the Twitter have any political sentiment or not, is it environmental sentiment, or what type of the sentiment this tweet have, a positive or negative sentiment. So these things you can include as the input feature. Thereafter you can estimate that how many people are going to retweet that particular tweet. The another important application of linear regression which we are going to use in this lecture, that is the real estate. In real estate, you can use the linear regression to predict the house prices. In the form of the input, you will be having house attributes as the input feature. So what could be the house attribute here? The house attributes are how many number of rooms are there in that house, how many bathroom is there, what is the area of that house, how far it is from city, how far there is a hospital around that house, how far it is from a highway, and what is the literacy rate around that house, what is the tax, and all those things you can take into the account for the house price prediction. So once you get all these features, then you need to feed these features in linear regression model. Once model is trained, now you will be able to predict these house prices based on your input. All right, perfect. So this is all about in this lesson. Thanks a lot for watching it. I'll see you next lesson. All right, let's go ahead and discuss what is regression type. How many regression types we have? We have two types of linear regression. One is simple linear regression and another one is multiple linear regression. And if we talk about types of regression, then you can say that simple linear regression, multiple linear regression, and non-linear regression. But here we are just looking for linear regression type. In fact, so I should say here this linear regression type. So these are the two types here, simple linear regression and multiple linear regression. So what's the difference between these two types of the regression? The first one, which is simple linear regression, it is actually one variable linear regression. That means in an input you have only one variable, and here for example only one variable which is house size is shown, and based on only one input feature or only one input variable, we are trying to predict the house price. All right. And if we talk about multiple linear regression, then we need more than one input variable. That means that is a multiple linear regression. All right. So this one shows that here there is only one variable and then predicted output. Thereafter, another one we have here intercept and better fit. So what is this? This says that how we are going to get the perfect line. All right. So how we are going to get here good fit, which is also defined as goodness of fit. A goodness of fit means how well or how good your model is fitting on given data. And this plot is showing you that how your model error is decreasing. For example, this blue line, do you see this blue plane actually? So this blue plane is actually a loss function. So this blue plane is a loss function, and as we are training our model, our loss is decreasing. So this one is like descending a hill. All right, that's mean you are going downward of a hill and then you are here going upward of hill. So you need to find here a valley. So the valley is this one. Do you see this? This plane is there. So the valley is this one, and this will be here a minimum error or minimum loss. So when you get a minimum loss or minimum error, then you say that your model has now fit the data. Simple linear regression can be defined as something like this. There you have an input variable which is x, and these are the regression coefficient. So this beta 0 is actually intercept. Alright, this beta 0 is intercept, and the beta 1 is a population coefficient, or you can say beta 1 is the coefficient of regression. It depends what type of the input we are actually giving to our model to predict the output. So this beta 1 is the coefficient of that particular variable, And thereafter you have here epsilon I, which is actually a random error. So this one is equation of a simple linear regression. In a simple linear regression, you have only one input as a feature. But in the multiple linear regression, you have multiple input as the feature. That means you have a multiple independent variable, or you can say you have a more than one independent variable as the input. Alright, this is also called as a polynomial regression as well, because we are including here a multiple input in a final output prediction. And if you notice here, in a simple linear regression, we get a straight line. But if we fit here a multiple linear regression, then we may get here a polynomial line as well, because we are using here a multiple input as the input feature. For example, if you notice here, we are using house size, and we are also using here number of bathroom in that house. So this one is the two variable. You can use as many as variable you want. It will be always a multiple linear regression there. And this price, their price is a house price prediction. And one more thing you may notice here, earlier we had here a simple line, but if you have a multiple input in your linear regression model, then you are going to fit here a plane. Alright, so in a single input you fit a line, but in multiple input you fit a plane. So with the two input you have a two-dimensional plane. So you are fitting this plane, and these actual house prices lies on these plane. Alright, that's how it works. You can include more number of features. So it's a kind of the unlimited number of features. As many input feature you have, you can include, and total number of features are equal to the total number of dimensions of this fitted plane. Alright, perfect. So this is all about in this lesson. Thanks a lot for watching it. I'll see you next lesson. Hi everyone. So we are now going to learn what is the Boston housing dataset and how we can load Boston housing dataset in our Jupyter notebook. So the Boston housing dataset have total 506 number of rows, and there are total 14 columns. And out of those 14 columns, 13 columns are an input feature which we will be using to predict the final output, which is the target output. These are the columns which is present in the Boston housing dataset. These columns are crime, GN, Indus. So before we describe all these things, let's go ahead and first load this Boston housing dataset. So the first of all, you have to install the packages here, R packages. The R package which we need here, that is the mass package. So it will install this mass package in your computer. Thereafter, we are going to load here library. Alright, so this mass package is loaded in your notebook. Thereafter, we can read it like this: Boston is equal to Boston. Alright, so this Boston dataset is read into a Boston variable. And if you see the head of this Boston, you will notice it has total number of 14 columns. Out of these 14 columns, these first 13 columns are actually input feature. And based on these first 13 columns, we will be predicting here the target output, which is the median value, which is the house price. And to understand the meaning of these columns, we need to visit here. We need to visit this description here. The crime is a per capita crime rate around the town, and GN is a proportion of residential land zoned for lots over the 25,000 square feet. So it's like that. What is the proportion of residential land there? Indus is proportion of non-retail business acre. This charge is Charles River dummy variable. Their NOx is nitric oxide. So it's like nitric oxide around the house. There you have RM, which is the average number of rooms. Then you have age. Age shows that what is the age of house. DIS, you have the weighted mean of distance to a 5 Boston Employment Center. Thereafter, you have here radius, it's the index of accessibility to the radial highway. Thereafter, you have the tax, full value property tax rate. Then you have here a PT ratio, which is the people teacher ratio by the town. So this says that what is the ratio of people living around that house and the teacher ratio. The more number of teacher presents around that house, means the better you can say the better accessibility for the education. Then this black says that the proportion of blacks by town. Then you have LSTAT, which is the lower status of the population. And the lower status of population means what is the percentage of the population, poor people living around that town and the house. Then the median value of owner occupied homes. So the moreover, what is the median value of a house price? All right, and it is the $1,000. That's when the scale of these median values are $1,000. So the first house price is 24,000. Another one is the 21.6 thousand. There you have a 34.7 thousand and so that. All right. So based on these input features, we will be predicting the target output. And you can also see the structure of the Boston housing dataset. This structure says that in fact, all these columns are integer and number. That's been the numerical column. You can also get those from here as well. Thereafter, you can also get the statistical summary of this data set, the summary Boston. So the summary Boston says that these are the statistical summary. And in statistical summary, if you notice, the maximum value for crime is 88 and lowest value is 0.006, which is almost none. GN have a 0 to 100, Indus have 0.46 to 27. And if you notice the maximum values for all the column, you will notice that there is a huge difference in the scaling of these variables. If you have a various scaling of these variables, then you have to also understand that the scaling of all these variables should be the same. Otherwise, those variables which have a large scale, those variables will influence the target output more. But we don't want that. We want actual variable which influence the target output. Then how would you know that which input variable is influencing the target output most? If you take one column one by one, each column, then if we calculate the correlation between the target output and the input feature, if there is a high correlation, either the positive or the negative, then we can say that this is the highly correlated and there is high probability that we can predict the target output, because we need a little correlation between the input and the output. If input and output are not correlated to each other, then there is no way to predict the output. So there has to be some pattern. In the next lesson, we will learn the correlation method. We will calculate the correlation between the input to input features and input to output features. Before we calculate the correlation, we need to first install few packages. So let's go ahead and install those packages first of all. We will be needing here the tidyverse package to analyze our dataset. So basically I'm going to do here install packages. You need to just write there install pack and then press tab. It will autocomplete install.packages. In that, I'm going to create here the list of packages which I want to install here. So I want here tidyverse. Then also I want here core plot, which is the correlation plot. I also want here the lattice, which we will be using for visualization. And do remember, with the tidyverse, you have already installed ggplot and dplyr package. So we have also installed the mass package. There is only one package which we still need in our coming lectures. In fact, two packages. One is CA tools. This package we will be using to split our data set. Thereafter, we have here this matplotlib package. Just run it, then it's going to install all these packages in your computer. Once these packages are installed in your computer, then we are going to load all these packages. There you have load tidyverse. Thereafter this library. In that library, I'm gonna do here lattice, then library plotly, thereafter library corplot, and then library CA tools. Just run it. It's going to load all the packages in your computer. All right, that's mean in your notebook. Everything is loaded. This core plot we will be using to plot the correlation data. Let's go ahead and plot this correlation data. So first of all, we are going to get here correlation matrix that we can get with core, and then you have this Boston. Just run it. Thereafter, what would you get here? You get here this core mat. This core mat says that, sorry, this should be core mat. This correlation matrix is actually the correlation between these variables. The list of variable here is also column, and the same list of variables are also in the rows. And one more thing, if you notice there in GN, perhaps let me see, it is perhaps in charge. So the charge value is quite low. If you notice, the charge values are quite low. Alright, so the lowest value is here 0.07. So it means the correlation of this charge to other variables are almost negligible. This is quite low. This is quite low. But if you notice the correlation of RM, this average room number, this one is almost average correlation. But with the house price, you will notice it has a high correlation, this one. All right, so there you have this RM. So there this RM is quite highly correlated with the target output. All right, and similarly, you will notice other variables as well there. And this median is also correlated with LSTAT here. This is also highly correlated, but this correlation is in negative correlation. That's mean when LSTAT, which is the lower status of the population, that means when the population of poor people are increasing around the house, then the house price is going to decrease. And this one was for average number of rooms. This one is the positive. That means when average number of rooms are increasing per house, then the house price is going to increase. The positive correlation means if independent variable increases, dependent variable will also increase. And negative correlation means if independent variable are increasing, then the dependent variable will decrease there. Let's go ahead and try to understand it with the plot. So for plot, we are going to use here this core plot, and in that we are going to pass our core matrix, sorry, this core mat. There I have, then I say just run it, and then you will notice here this core mat is giving us a full matrix here. All right, so in the full matrix, these number, all right, these actually the circle shows us that if it is the darker in the blue side, that's when the blue dark color means the positive correlation, and the diagonal elements is of course 1, because the correlation with the same variable is of course will be always 1, because if you notice this charge to charge there is 1, and the correlation with any other variable is almost negligible. So this charge is the least important parameter in our data set. Thereafter, this negative correlation, that's the minus correlation. These variable, if you notice, are quite dark and red color. So these are the reddish dark color. So these reddish dark color are producing here
the negative correlation. The negative correlation means when these values will increase, the dependent value will decrease. But we are interested to analyze the correlation between these variables and the target output. The target output is the median value of a house price. This one is the blue color, and the larger circle size means there is a high correlation, and this says that the RM, that's when the average number of rooms per house is high, then the house price will increase. This one is the positive. The another one we have here negative. That's when it says that LSTAT, if a lower status of the population increases, then the house price will decrease. And thereafter we have other, like here a crime. So crime, of course, if crime increases around a house, then the price of that house will decrease. And other variables are not much important, like here you have a distance and charge. So these variables are not much important. You have another variable like index, nitric oxide. So of course, if nitric oxide increases, house price will decrease. There you have here this radius and PT ratio. So of course, if PT ratio increases, that's mean the people to teacher ratio. The people to teacher ratio will increase when the number of teachers are less around that house. That means the house price will increase around that house. Alright, perfect. So this is all about in this lesson. Thanks a lot for watching it. I'll see you next lesson. Alright, so the first of all, now we are going to do here crime analysis in Boston. So basically, if you remember previously, we had seen there is a column which is known as a crime column. This crime column says that what is the crime percentage happening around that city. Alright. So there is error, this error is coming, and this error is a quite common error. Whenever you are working with your Jupyter notebook and you get something like this, then you can simply restart your kernel. So you need to just restart your kernel. Once you restart, then I think this error should be gone. Let me see it once again. So still that error is coming. So to remove that error, I just want to show you intentionally. Whenever you get that type of the error, then you need to just stop your notebook, come to your Anaconda prompt from where you had started your Jupyter notebook. You need to just stop your notebook. Alright. You need to press there Control and C if you are working on if you are working on Windows, and you need to press there a Command and C if you are working on Mac. Just restart it once again. So this is going to just restart. So everything will be as it is. I don't think now there is any problem. You need to just restart this. Click on there. Thereafter this will be gone. Alright. So you can just load it. This package is already installed in our computer. I'm just running it once again so that you can see it. There the another one. There you have got the head. Then this one, and thereafter just run it. Alright. So we are going to do here crime analysis in the Boston. So the first of all, we are going to see here the summary. So for the summary, you can get something like this. Boston crime. You need to just write here Boston crime. This says that the minimum value of crime is 0.00632. The maximum value we have here 88.97. Alright. So from the correlation matrix, we had already seen that there is correlation with the crime and tax, radius, and LSTAT. So of course, if the lower population, the status of the lower population, the lower population status is quite high in that area, then there is a possibility that the crime rate is also high. The radius and the tax rates are also high there. Alright. So what we are going to do, we are going to analyze especially this tax and LSTAT. Alright. So we'll be seeing that what are the effect of tax LSTAT on the crime. So for that, we are going to first plot here with the plotly. So there you have here our plotly. So there you have a plotly. In the plotly, we are going to pass here the data is Boston dataset, and x is equal to, we are passing here LSTAT, and then we are going to see that how our crime is actually changing as LSTAT is changing. So the type of plot we are going to see here, the scatter plot, and then the mode we have to give here the markers so that we can get here the scatter plot. All right, so there you see here what we are getting. There you have LSTAT crime, and if you notice, if this LSTAT is increasing, then there is a possibility that the crime is also increasing, and you will notice that there will be a positive correlation between the crime and LSTAT. Do you see there the positive correlation? You can also verify that with the correlation matrix. There is a crime, and then we have here the first row is crime and then LSTAT. So there is a positive correlation, and we can verify here that as LSTAT is increasing, the crime rate is also increasing. Let's go ahead and see how the radius is changing. All right, so the radius was actually, if you notice there at the start of this lecture, we had here this radius. Radius was index of accessibility to radial highways. All right, so here you need to just write here this plotly, and in the plotly, in fact, I can just copy this whole thing from there, and then I can paste it here, and at the place of y, this is going to be the crime, and at the place of x, I'm going to change here this radius. So I just want to show you that how this crime is correlated with other variable. So with the radius variable, you will notice that there is high, all right, so there is high crime when the radius is quite high. All right, so when the radius is quite high, then there is a high crime. So there is high crime. And when you have a smaller radius to a nearest highway, then you have a less number of crimes there. Similarly, we are also going to check here. We are also going to check it here with the taxes as well. So you need to just put here the tax. This tax says that it might take a while to plot it here. So once again with the taxes, we also get there when the taxes are high. When the taxes are high, then also there is a high crime rate. All right, so when the taxes are high, then also crime rate is also high. All right, so what we understand here that there is the high crime here. All right, so as radius is increasing, crime is also increasing. As taxes are increasing, crime also increases. As LSTAT increases, crime also increases. So we understand with this analysis how this crime is increasing with comparison to LSTAT, radius, and the taxes. In the next lesson, I'll show you where top 10%, where the top 10% crimes happen. I mean to say that how the top 10% crimes are correlated with other variable. All right. All right. Now we are going to analyze the top 10% of the crime rate. So moreover, if I say the top 10%, that means I want to get the crime rate where the top 10 means the crime rate after 90th percentile. All right, so you can understand it like this. If you search here the quantiles, there you will get something like this. All right, so there you get if something is more than 90%, then those cases are rarest in rare. And we need to just understand here after the 90% of the quantile. All right, so we assume that it is normally distributed. Even though if it is not normally distributed, we are moreover interested in top 90%. All right, so the top 90% quantiles. So I'm not able to get here the, yeah, there you get it here. So this, let's say this is one, this one is the 90th quantile, and after this 90th quantile, these are the rarest. So we need to understand that what are the cases where the highest crime rate happens, all right, after 90% or 90 percentile. All right, so for that you need to understand it like this. If I say the summary of crime, which we can get with the Boston for crime, there you get this one is the third quantile, and this one is the maximum value for a crime rate. So the third quantile means this one is 75th. All right, this one is the 75%. So the 75% of the crime rate are below than 3.67, and the top 25% are those crime rate which are in between 3.67 to 88.97. But we are interested in the top 10. That's mean we want here the 90th quantile. So that we can get it like this: Boston crime and then 0.9. So there you get this value. So the 90% is 10.75. So their crime rate you have 10.75, something like this, and thereafter these values are highest. So these values are top 10 highest values. Now we want to filter out these values, and thereafter we will analyze these values where these values are happening. So for that we need to get here the high crime. So you can get here H crime, that's the highest one. Then we are going to get it with the subset. Do you remember previously I had also shown you, you can also filter out the data by using the filter as well, but here I'm going to just use the subset as well. So there you have crime, and then I say the crime is actually greater than with this value. So simply I'm going to just copy that value, and then I'm going to put it here and just run it. So once I run it, and thereafter if I notice this H crime, there you will get total 51 rows. So there are 51 instances where we have the highest crime rate. And if you notice, these crime rate are greater than 10.753. Now we need to understand what are the correlation amongst these variables if we select the top 10% of the crime rate. So for that we are going to first of all get the summary of this H crime. So the summary you can get simply like this. There you have the minimum value, and there that one is the maximum value. All right, so other the summary for other statistical variables are also here. But let's go ahead and plot the same plot which we had plotted earlier. So the plot something like this. Let's say you have a plot like this, and that plot, if I plot right now, you will notice this plot there, a crime rate where you are getting, this Boston should be actually H crime. Alright, so there you have greater than the 10, and now it is distributed something like this. So there still we see there is some upward trend even after this one, the top 10% quantile, top 10% of the crime rate. But the moreover, it is almost, you can say it's uniquely distributed between these 10 to 35 of LSTAT. Let's go ahead and plot here a box plot to understand it in more better way. That I say here this plotly, the data is equal to the Boston. So I'm just going to compare it with the Boston data set and with the current data set, which is the top 10% of the crime rate. Then I say here y equal to LSTAT, and I'm gonna give here the name as full Boston data, and the type of the plot which I'm gonna plot here, that is the box plot. And thereafter I'm gonna put here our pipeline operator. That's mean we are going to continue this operation in the next line. There I'm gonna add another box plot. So this is the method to add multiple plots in a single frame. So there you have add box plot, and there I'm gonna put here. In fact, what I can do, I can simply copy this whole thing and then I can paste it here. And this Boston, I'm gonna change it to the H crime. And this name should be the current data set, which I say 8 area with 90th percentile. All right, so there percentile crime rate. There, this one is H crime. When I say the area, there if you notice, we are actually plotting it against the LSTAT. So the LSTAT is actually the percentage of the lower the status with the lower status population. So the lower status population area, we are actually interested in what will be the crime rate if we plot it against the LSTAT. All right, perfect. So let's go ahead and just plot it, then you will understand. It says that some error is somewhere, perhaps here. That should be actually H crime. All right, so if you plot it, then you will notice there a difference is that this one is the full Boston data. In the full Boston data, you have LSTAT, the average LSTAT is somewhere here. All right, and this data is against the all right, so this data is against the crime, and this one is also with the filtered crime. So the moreover, this box plot is actually univariate. You don't have a crime data here in the axis, but if you notice, this one is the average LSTAT is coming somewhere here. All right, but if you notice LSTAT distribution for those area where crime rate is the highest, you will notice that the status of lower status of the population is quite high there. All right, so the lower status of the population is quite high there. That means this data suggests that there is possibility that crime happens more often in those areas where the people are living, the lower status people are living. All right, thereafter, and you can also plot here our median value. So there I say med value. All right, so there I'm gonna say here med v, and there I'm also gonna plot here the med v. So this med v is going to plot the house prices. So the distribution of a house price is quite high if we take all the data set. All right, on average for all data, and the house price is quite low if we take those data with the top 10% crime rate. So it clearly suggests that, what is the conclusion? So the conclusion is that the mean crime rate in the Boston is 3.6. All right, so how would you get that? Let me once again bring the summary here. So there I get the summary for the Boston. So this says that the mean crime rate is the 3.61 and the median crime rate is the 0.23. So there is a high difference between the mean and the median. That's when the distribution is skewed distribution. And the second point is there are 51 rows or 51 houses in the Boston that have very high crime rate. The crime rate is above 90th percentile. Majority of the Boston suburb are Boston areas where the crime rate is high. The lower status population is also quite high there. And where the crime rate is high, the house prices are also low in those areas, there is a correlation between the crime rate and the portion of the population with the lower status. So in the last point, you can also conclude that house value suffers greatly from the crime rate. So those areas where crime rate is less, then the house prices are high in those areas. Alright, so this is all about in this lesson. Thanks a lot for watching it. I'll see you next lesson. Alright, now let's go ahead and do a portion of population with the lower status analysis. Previously we did analysis for crime, and in this lecture we will do the analysis for the population with the lower status. We will be also taking the account here median value, that's the house prices, and we will be also taking here average number of room and the age of a house. If you remember with the core mat, there you need to just write here this correlation matrix. It says that here with the lower status of here this one, the population with the lower status, there you will notice that the median value, that's mean the house price, is negatively correlated with the LSTAT. And other than that, you will also notice that the average number of room here, alright, so this one is also negatively correlated. That means there is negative correlation, and age is positive correlation. So it says that those houses which are actually aged, or you can say those houses which are old, the status, the lower status population is quite high in those area. So basically we are going to do a same analysis which we did earlier. So I'm just gonna copy this one. Alright, and then I'm gonna paste it here. So what was this? This was, we are plotting here the LSTAT and the Y was crime there. But right now we are going to plot LSTAT, and there are three variables we have: house price, room, and age. So the first of all, I'm gonna see here mid-V, that's mean the house prices, and we want to see that how this house price is correlated with the lower status. Alright, the population of the lower status. There you will notice there is a negative correlation as the population with the lower status, increasing, the house prices are decreasing. This one we have also proved earlier that if LSTAT, that's mean the population with the lower status is high, then there is a high chances that the crime rate is also larger and house prices were also low in those areas. And this also proves the same thing there. Let's go ahead and see how we can verify here with the RM. So how average number of room is correlated with the population with the lower status. So this one also says that here, though we don't have exact, but still there is a downward correlation. So as lower status population is increasing, alright, lower status population is increasing, the average number of rooms are also decreasing. Thereafter we have this last one which was actually age. So with this age, there you will notice as lower status population is increasing, the house age is increasing there. Alright, so there you have a positive correlation. So what is the conclusion with these three graphs? These three graphs says that those houses which are old, that means there the population with the lower status is high, and those houses which have larger lower status population, there is possibility that average number of room will be less and house prices will be also less. Alright, so in the next lesson, I'll show you the top 10% of lower status population. I mean where the poorest people are living, we are going to do the analysis of those areas. Alright, I'll see you next lesson. Alright, now we are going to the analysis of those areas where the poorest people are living. That means we are going to get here the above the 90th percentile, those areas which are above the 90th percentile of the LSTAT. So we need to first get here the summary. So there we get the summary for the LSTAT. The summary says that there you have the population with the lower status, the index, this one is actually index. So the 75% of the population is below the 16.95, but we are interested to get the 90th percentile. So there we get there this quantile, and in the quantile we just need to write here the Boston and the name of the variable where we have LSTAT, then 0.9. So the 90th quantile is here, this one, actually 90th percentile is 23.035. So we need to get those areas which have a lower status population index greater than 23.035. So we can simply just copy it, and thereafter we are going to do here the subset analysis. In the subset, we have here the Boston dataset. Thereafter, we have here this LSTAT greater than quantile Boston LSTAT 0.9. Alright, that's the 90th percentile. So once again we are getting total 51 rows. Earlier we had also seen that there were 51 rows, and currently we also have a 51 rows. That one I'm gonna say here as lower status HLSTAT. Alright, so this one is HLSTAT. There are total 51 rows are there. So once again we are going to get the box plot which we had seen previously. So just for the simplicity, I'm gonna get it so that we can plot it easily. So we need to just paste it here. Now we are going to compare the attributes between the high LSTAT, that's mean where the poorest people are living, and with the original Boston dataset. So the first of all, we are going to analyze the house prices. So there we get the LSTAT here. Alright, sorry, this one is the high LSTAT, that's the HLSTAT which we had just got here, and just run it. Alright, so alright, this should be actually area. If you remember previously I did that analysis, I think it was wrong here. That should be area. Alright, so correct it. Perfect. So there you have the area with 90th percentile. This should not be crime rate, but in fact this should be the LSTAT. Alright, I think everything else is same, so we don't need to worry about this. Just run it. So once you run it, you will notice here the house prices with the where the population of the poorest people are high, the house prices are less in that area, and this is a logical. All right, thereafter if you try to plot here the average room which we had seen earlier in our scatter plot, this one is going to plot the average number of room. So once again you see there the average number of room in those areas where the lower status of population, that's mean the top 10% highest lower status population index, there you will get the lowest number of average room per house. And on average, this average number of room per house is quite high, which is actually perhaps 6.2. That's the 6.2. But in this case, we are getting somewhere the median is, let me see. The median is 5.97. Yeah, there 5.46. All right. Perfect. Let's go ahead and try to do the analysis for other variables. After this average room, we are going to also do the analysis for the age as well. So there I do age, and then also I do here age as well. Thereafter, with the age, we get those house areas which have highest lower status population index. The age of those houses are quite high, but it's quite high. That's mean there the houses are built almost 100 years ago. So it's something like that. Let's go ahead and see the crime analysis. So if you do like this, there is the crime analysis for whole data, and with the top 10% of the lower status population. All right, so this one says that there the crime rate is also high. So the crime rate is also high in those areas where the people with the lower status are living highly. All right, that means the index of the lower status population is high. That means the house price is going to be low, the crime rate is going to be high, age of the house is also going to be high, and average number of rooms are going to be low there. So in the conclusion, what we get here, the fourth thing we get here, the first, with those areas where the population of the lower status is high, we get low house prices. We also get low number of average room per house. We get high age, that means houses are old in that area, and crime rate is also high in those areas. You can also do here the analysis with the nitric oxide as well. Alright, so it was NOx there. If you do this analysis, then we get here the fifth analysis. So this fifth analysis says that the nitric oxide is also quite high where the population, lower status population index is high. Alright, perfect. So similarly, you can do the analysis for other variables as well. So since we have done here the analysis for the two variables, once the first we did with the crime variable and another one we did with lower status population variable. You can also try it with the rest of other variables. In the next lesson, I'll show you how we can get started with linear regression. Alright, now we are going to learn about the single value linear regression. Alright, so it's like this single value linear regression. Let me just cut this one. So this one is the single value linear regression. Otherwise, you can say here the simple linear regression. Alright, so this one is the simple linear regression. Thereafter, we will also learn there multiple linear regression. So if you remember at the start of this lecture, I told you the types of linear regression. So there we had a simple linear regression and multiple linear regression. In the simple linear regression, we take only one input feature. We take only one input feature, and based on that input feature, we try to predict the target variable. But in the multiple linear regression, we take some multiple input and we try to predict the final house price. So the same thing we are going to study here. We are just going to take only one input variable. That only one input variable could be anything, but we always try to take only those variables which have high correlation with the target output. So if you remember with our core math, which was the correlation matrix, this says that LSTAT and average number of room have high correlation with the median value of the house. There you will notice this one have minus 0.7376. That is the negative correlation, but yes, the value of correlation is quite high with the house price, and average number of room per house, that value is also quite high. So here I'm going to select first of all RM, thereafter I'll also show you with the LSTAT as well. Alright. So we already have our data set in the Boston. So the first of all, we need to divide this Boston data set into a training set and testing set. But before that, we also need to test here, is there any null values in the data set or not? That means we also need to do here the pre-processing of the data set. So how would you check that if there is any null value? It's like this. You need to just type there any is.na, and then you can say there a Boston. So if there is any null value, it will be true, otherwise it's a false. Let's suppose that if there was any null value by chance, then how would you remove that null value? It's a pretty much simple. You need to just write here a which is.na, and then you need to write here the Boston equal to true. Alright, so which are true, then we are going to get those index. Alright, so there you get here number of NA, and once you get that, then we say here if this number of NA is greater than 0. So we are just gonna put it here. If these number of NA is greater than 0, sorry, I should say here number of NA is greater than 0, then I say this Boston equal to the Boston data set, and then I say this one, the complete dot cases, and there you get the Boston, and then we need to select all those index. So this one says that this one will give the index which are complete, that's mean those index which do not have any null values, and thereafter we are selecting all those indexes and the comma, and we left it as empty. That means we are getting all the columns. Just run it, and it says that here it is this one error in there, argument is left 0. So let me see what's happening there. Just a second, let me. Alright, there is one issue. Actually, this should be length there. So we need to write here this length. Alright, so there we get, even you can check here number of NA, it says that 0. That means there is no null values present in the data set. Let's go ahead and split the data set. So we say here set dot seed, and we are going to set it 0. So why we set the seed here? Set seed is like a random number generation value fixing. That means you cannot generate random number in a computer. You may see that random number is being generated in your computer, but if you set a particular seed value, then you will always get a same number. So if I set here set dot seed equal to the 0, that means even if you set a set dot seed equal to 0, then you will get exactly the same result as I am getting. So it will help you to diagnose your data and your machine learning model. So there I say split equal to sample dot split, and then I say here this Boston data set and split ratio equal to 0.8. Alright, so there you have got this one, and thereafter this split gives you here the index. Do you notice there this one is index, and now we are going to get these index values by typing here the subset of the Boston data set and get those data set where split is equal to the true. And similarly for the test data set, I get those values where split equal to false. So I say this one as the trained data set. Otherwise I can just say here this one is the X trained data set and this one is going to be the X test data set. Alright, so this one is the trained data set and this one is going to be the test data set. In fact, this one is not X test, but in fact this one is the trained data set because X and Y both are included in that. So it's both data set, trained data set and test data set. Just run it and now we get here the head of the training data set. In that we get total 14 columns. So this last column is actually the target variable which we will be using as the predicted variable. So what we are going to do here, we are going to write our linear regression model in just a single line of code. It's very simple. It's very simple. So I say there model equal to LM, that's the linear regression model, equal to med_v. This one is the house price. That means this target variable is this one. And then we are going to take input variable. So for taking the input variable, we need to give there LSTAT. So how it is deciding? This tilde operation says that these two variables are disjoint and this one is the independent variable and this one is also now independent variable. But this one is actually depending on this one if we see on the data set. But the moreover, these data set which are after this tilde operation is being passed as the input feature and this one is being passed as the target variable. And thereafter we put here in the input data equal to trained data. So in the training data, this LSTAT is the column of this LSTAT values and median value is actually values of these column. And if we just run it, our model is trained and it is saved inside this model variable. And simply you can get the summary of your model variable if you just type there summary model. Perfect. So you get here a many variable information. So what are those variable information? There you get here. This says that call, that mean to say that we used this formula to calculate this model. That's mean we used this formula to train our machine learning model. These are error. So residuals, that's mean this one is error. So the minimum error in our model have -15 and the maximum error we have here at 24.5 and the median error we have a -1.38. The coefficient of the variable there for LSTAT, the intercept we have 34.55 and the coefficient for the LSTAT we have -0.95. If you remember, the correlation variable was also in a minus for the LSTAT. That's mean if there is a minus value, that means if LSTAT is increasing, then the house price will keep decreasing. All right, perfect. And these are the some of other error types which we will discuss later, like the standard error, t-values and the p-value. The p-value is the probability of a particular value. This number of stars says that how important that particular feature is there. If number of star is high, that means this particular feature is quite high. I mean the importance of this particular feature in calculation of the target variable is quite high. This one is also significant coefficient. The significant coefficient also says that there is the 3 star. That's mean it's a quite high value. And there you have the residual standard error. This says that the residual standard error is 6.216. This one you can say that like the RMSE, root mean square error. Thereafter you have the R square value, which is 0.54, and adjusted R square for 0.5432. But do remember, this one is on the training data set. We need to understand what is happening for the test data set. Alright, so for the test data set, what we have to do here, don't worry about other variables. In the coming lecture, I'm going to first discuss about these variables. What is the t value, what is the p value, and thereafter once again I'll come back to this lecture. I'll come back to this model and then I'll explain you what are these values and what are the significance of these values. But first, let's go ahead and train our model on the, let's go ahead and predict the values for the test data set. So one more thing you need to understand here, we train our model on the train data set. We test our model on the test data set. So we need to here, first of all, we have to include here the library. So the library, we are going to include here the metrics library. So this metrics, let me see what is happening here. This seems like metrics is not installed. Packages. This should be install packages, and in that we put here this metrics. So it's going to first install metrics package and thereafter it will include that metrics package. Thereafter we are going to do here the predict. So the predict model on the test data set. There you will get these prediction. So this one I say as the predicted value, and then this predicted value we need to pass here this RMSE, root mean square. So there I say here this evaluate, this one we are going to do for the predicted value. Alright, so there you get this spread value, and then we pass here our test data set, all rows with the 14th column. So what does this mean? This means that we need to get the RMSE, this one is the predicted value, and then we are passing here the target variable, which is the 14th column, which was actually the median value of house prices, which was actually the last column if you remember. The 14th is last column. Then it is going to calculate here the RMSE, that's the root mean square error. Alright, so what is the root mean square error? It's like the difference between the two values and then square it and then sum for all these values and then take the root square. Don't worry, in the coming lectures I'm gonna explain you these things in very detail. So there you get it. So we are now getting here 6.20. This one is the RMSE for the test data set. Alright, so the first of all, now I'm going to explain you what are these values and how we get the statistics of model. Alright, thereafter we will again come back to these statistics and then we will try to understand that what is the meaning and the significance of these values, like what is the t value, p value, adjusted R square and R square, RMSE, all these things first of all you need to understand. Alright, now let's go ahead and try to understand how we can diagnose our linear regression model. Previously we had seen so many statistics and we don't understand what are these statistics and what are the significance of these statistics. We don't know if there is high value or low value for any of these statistics. So whether our model is good or bad. So we need to first understand those things. So those things we are gonna decode here in this lecture. And I should first warn you that this is going to be a little boring lecture, and you should have a patience. And if you are not able to follow this lecture, you can stop it and then you can watch it after some time. Otherwise, you can watch it in a break, like you can watch it for 2 minutes and 3 minutes and then try to understand what I have just explained you. Thereafter, you can also take for some more time to grasp these information. You can read on the internet, etc., to understand these things. These things are a little complicated and you need to just pay here a little extra attention. So let's go ahead. First of all, start with p-value and what is the significance of the p-values. If you notice, previously we had seen there, we have this one is the probability of being as a p-value. So this one is actually a p-value and this one is the t-value. So we need to first understand what is the p-value and what is the probability of what is the t-value, and there you have also p-value. All right, so what's the p-value? You need to first understand what is the hypothesis, null hypothesis. So let's go ahead and come back here. What is the null hypothesis and alternate hypothesis? Once you understand this one, then we will again come back to our p-value. So there are actually two hypotheses, a null hypothesis and alternate hypothesis. A null hypothesis means something which does not change any status. All right. And in case of our linear regression, what is the null hypothesis? The null hypothesis is that the beta coefficient, the coefficient which was actually causing to increase or decrease the final target output. So the beta coefficient is associated with the variable is equal to 0. If you remember, previously we did the analysis for the simple linear regression and a single value that was for LSTAT. So for LSTAT, we had here the coefficient for LSTAT is minus 0.95. So in the null hypothesis, it assumed that this coefficient is equal to 0. So this one is the null hypothesis. So why this is null hypothesis? Because by default, when we don't have the model, then the coefficient for every model, every input data is equal to 0. So the null hypothesis says that there is no change, and we assume that that is the null hypothesis. And in the alternate hypothesis, what we have, we try to disprove the first hypothesis, which one is null hypothesis. So in the alternate hypothesis, we try to disprove this null hypothesis. That means in alternate hypothesis, we say that the coefficient of the associated variable is not equal to 0. That means it is either greater than 0 or less than 0. So you just try to understand it with this figure. This figure says that, let's say you love a girl and you are quite engaged. All right. Otherwise, you can say both of you are actually a friend. All right. So in that case, there is some status. The status is maintained there, whether you are a friend or you are engaged. Otherwise, let's assume that you are just a stranger to each other and you have just met to each other. And you just propose that girl, whether you want to marry her, otherwise you will propose it to be a friend. So whatever you propose with the girl, then when you met that girl, there is some status. If you have not met each other before, that means both of you are a stranger to each other. That status is a stranger to each other. And if that status after your let's say once you propose and that status does not change, that means there is a null hypothesis. That means you propose a girl and girl reject. That means there is no change in the status. If you are a stranger, you will be stranger because the girl has rejected. If you are let's say already engaged and you proposed for to be married and girl rejected, that's mean you guys are still engaged. That's mean there is no change in the status. That is the null hypothesis. So in the alternate hypothesis, you just try to disprove the null hypothesis. That means you try to disprove the no change in the status. So if alternate hypothesis is true, then once you propose the girl is going to say the yes. So when girl says yes, that means you are rejecting here this null hypothesis. That's mean there is no change. I told you at the start of this lecture, this is going to be a little complicated, but if you think about this whole process, how it is happening, I'm sure you will understand what is this null hypothesis and the alternate hypothesis. So in the case of our model, we assume that there is the zero coefficient. There is a zero coefficient. That's mean if there is no model, we have just started training our model, then at that time the coefficient of that variable is 0, since the model is going to learn, and that is the null hypothesis. And in the alternate hypothesis, I say that when the model will learn, then this coefficient will not be equal to 0. Alright, that coefficient will not be equal to 0. That is the alternate hypothesis. So in between this hypothesis, null hypothesis and alternate hypothesis, there is a lot of training is going on behind the scene. So there we come with the p-value. So how this is happening here? Let's say you have the distribution of your data. Sometimes what could happen there? Sometimes for some instance, your coefficient will be equal to 0. In that case, your value, when the coefficient is equal to 0, that's mean null hypothesis is correct. And for some cases, your coefficient is not equal to 0. In that case, then you have rejected the null hypothesis and the alternate hypothesis is correct. So the distribution is just something like this, and 95% of the chances that the data falls in this region, and there is just 5% of the chances is there when the data falls in these areas. That's mean you are saying if there is a normal distribution and these values are 95%, this positive and the negative words, then these are just chances of the 5%. So in these area, you say that there is very small chance that the null hypothesis is going to be correct, and there you have very small chances that null hypothesis is going to be correct. But the 95% of the chances are there when you can say that the null hypothesis you have rejected, means your model have rejected the null hypothesis and your model has followed the alternate hypothesis. Alright, so in that case what happens, that 5%, if you notice there, if the p-value is less than 5%, the 5% is 0.05. That's mean if the probability of being true of the null hypothesis is less than 5%, then you will say that that particular feature is important for your model. Let's go ahead and try to understand it one more time. So let's suppose that you have here LSTAT, and there is, if just a 5% chances or less than 5% chances that the coefficient of this LSTAT is going to 0, in that case only you would consider that LSTAT is important. But suppose that if 50% of chances that the coefficient of LSTAT is equal to 0, then I don't think that there is any importance of this LSTAT, because the most of the time the coefficient of LSTAT is equal to 0. That's mean it is not contributing in the prediction of the target output. And when this LSTAT is the coefficient probability, you can say it's like the probability. If you now notice here, this one says that the probability of being less than 5%, the 5% less than 5% is 0.05. so what's going to be the probability of less than 0.05? There you will notice that even it's the probability is less than 2 into 10 power minus 16, so it is way less than 0.05. so it says that this LSTAT is actually very important. All right, and there is the t value. So the t value is something like these values are there, t values. All right, so you need to just understand it a little bit more. So what you would understand with these two headings here. So it says that the larger t value means that there is very high chance that you will reject the null hypothesis and you will accept the alternate hypothesis. So the probability of very high t, says that you get a t value as high or higher than the observed value when the null hypothesis is true. All right, so in that case, when the probability of high t is low, all right, that means the probability of high t is low, then you have a better model. So the moreover, it says that when the probability of high t is low, then you have a better model. When the probability of high t is high, then you are accepting the null hypothesis. But when the probability of high t is low, then you are rejecting the null hypothesis and you are accepting the alternate hypothesis. The alternate hypothesis says that the coefficient of the regression coefficient of that particular variable is not equal to 0. That means that coefficient is important. So the less than 0.05 value, that's the p value, less than 0.05 p value says that coefficients are important, and if you have the p value for any coefficient greater than 0.05, then you can safely discard that coefficient, because that coefficient is not important for us. So the moreover, we can set here the threshold in the selection of variable as 0.05. all right, so moreover, you need to just understand the overall whole process here, that the t value should be high and p value, the probability of being t high, is low there. All right, so this t value is high and the probability of being t high is low is good for us. When t is high, probability of t high is low, then our model is most significant model. And this star says that how significant a particular feature is for the prediction of the target output. Alright, so in the next lesson, we will see what is the multiple R square, what is actually the R square, and what is the adjusted R square values. Alright, I'll see you next lesson. Alright, now let's go ahead and try to understand what is the R square and adjusted R square. If you notice in the summary of our model, we had there two values for R square and the adjusted R square. And you will notice a little difference between the R square and the adjusted R square. Let's go ahead and try to understand what is this R square and adjusted R square. So you need to first understand this explanation of the R square, what it says that. Let's say you have independent variable, you have here a target variable, and this one is the regression line, which is the y-fitted line. And then you will get the mean value of the output. Alright, so that is the y mean, and this one is the fitted line. And let's say you have got here the actual y value, and you will get all the predicted value on these line only. So there is the difference between the predicted value will be always on this line. So the difference between these predicted value and the actual value is residual there. All right, so this residual, if you do the square sum of these residual for all the data point, that is the residual sum of a square, which is also known as RSS. So these values are actually RSS, and if you notice the difference between the actual value minus the mean value, that is the total sum of a square, which is known as the TSS. Alright, and then there is the predicted value minus y mean value. Alright, so this one is the mean value of the target variable minus the predicted variable, which is known as the square sum of these values are known as explained sum of square. Alright, so you have here the TSS, this one, the total sum of a square, then you have here residual sum of a square, and you have there explained sum of a square. So these three values we are going to use in the calculation of R square error and the adjusted R square error, and this one is known as the intercept. If you remember, in the summary of your model you will get an intercept. So when you are fitting any line on the data, then you will get this intercept, and the slope of this is being defined by the coefficient of that variable. If coefficient of variable is 0, then this line is going to be a constant line. If coefficient is the positive, then this is going to be in upward direction. If coefficient is a negative, then it is going to be in negative direction, that's meaning the downward direction. So the R square is 1 minus RSS divided by TSS. So this one, 1 minus residual sum of a square divided by the total sum of a square. So this one is the R square. So there you have also got this information, the whole information I have written here in the form of the equation. But let's go ahead and try to understand what is adjusted R square and why we needed adjusted R square when we had here R square. So what was the problem with the R square? See, this R square says that how much variance is being explained by the data. Alright, so let's say you have these predicted variable, predicted data. This predicted data, the variance in that predicted data explains the information about the target variable. Alright, so what happens there, once you add the data, more number of the data, then what happens, this R square increases, because if you notice there, this R square is 1 minus RSS divided by the TSS. So this TSS is total sum of a square. As you increase the number of data, this total sum of square will always increase there. Alright, so this one is the mean value, there is the actual value. So this total sum of a square value will always increase, as this line is going to be something like this. So in that case, what happened, when this TSS tends to infinite, then this value tends to equal to 0. So the moreover, even though you are not able to fit a good model, but if you increase the number of data, then your R square will increase there. But that is not desirable, because we want to fit our data correctly. We don't want to just increase the R square. So to just adjust that more number of data, we created there, I mean to say that the scientists created that adjusted R square. So in the adjusted R square, that more number of data which is added to the data set is adjusted there. So the adjusted R square is calculated something like this, 1 minus MSE divided by MST. So what is this MSE? MSE is mean square error. This mean square error can be calculated as RSS. The RSS, if you notice, is residual sum of error, that is RSS divided by n minus q. Alright, so this n is actually the number of observations and q the number of coefficients in the model. So the q, if it is a simple linear regression, then there is only one coefficient, and n is says that how many number of rows are there. So once you start increasing your number of rows in the model, this will keep balance on the RSS. Alright, let's go ahead and see what is this MST. MST is TSS divided by n minus 1. I told you earlier that when n tends to infinite, then TSS also tends to infinite. But here it brings the control there because it has just divided it by n minus 1. So the n is the number of observation there. So TSS tends to infinite, then n tends to infinite. There is infinite divided by infinite. Then you need to apply here the L'Hospital rule. Then moreover, it says that when we increase the number of data in our observation, it is going to balance our TSS. So this one is the MST, which is the mean square total error. And this one is the MSE, which is the mean square error. Alright, so if you remember previously, we had their MSE. So MSE, I think we have here, this one. Alright, so this was the MSE. The MSE is there, the sum of these square error divided by the number of observation. That mean to say that that is the root mean square error. Alright, so that's the, you can say the average error you are getting. Alright, so this is all about in this lecture. Alright, so we have understood the process of these metrics, evaluation metrics actually. So we are just going to understand it once again here. So this one says that the residuals are error there, and the minimum error is minus 15, maximum is 24 there, and we have the p-value is less than 2 into 10 power minus 16. That's when the significance being significant of this this variable is quite high there. And thereafter you have the F statistics, which is a square root. Alright, this one, sorry, this instead of this F statistics, there you have the residual error. This one is the MSE actually. Alright, this residual errors are MSE there. Multiple R square. This one R square is 0.54. The high R square and adjusted R square is preferred there. If there is a high R square, that means you have an important model there. Alright, so we have also tested here on the test data set. We have got the 6.20, or you can say that 6.2 for our RMSE on the test data. Let's go ahead and try to evaluate it further, and I'm going to just do it after our explanation of evaluation metrics. The first of all here, I'm going to take our LSTAT. So let's say if you want to predict the target output based on this LSTAT. So in the LSTAT, I say there, just a second, there I say the data frame, and in that I say the LSTAT equal to 1 to 30. Alright, so 1 to 30, I'm going to just create here a 30 values. And based on these 30 values, I want to predict the target output. So there, this one I say as the data. There you have got the data in the form of the data frame. And at the same time, we are also going to give here the median house prices. Alright, that's been the predicted value that I say here, med V equal to the predict for model, predict with model for the data dot frame. Alright, and I'm just gonna put here this same value there as well, this one. Alright, so predict it for the data dot frame LSTAT is equal to 1 to 30. There, once you do this one, you will get the data, this LSTAT, and the predicted house price for these LSTAT values. Now we need to analyze these values. So I'm going to use here this plotly. In this plotly, I'm going to pass this plotly as the with the pipeline operator, and then I'm going to use here this add trace here. Add trace, in that I pass there x equal to LSTAT, that's the LSTAT data, and then I say here y equal to medv, that's mean median house price value, the type is scatter plot, and then mode equal to, we are gonna set as markers mode. All right, in fact, the type I'm gonna set it as a line. Sorry, this type will be that, the mode will be here a lines mode. All right, thereafter I also need to pass here the data. In the data I pass as the data, and name I say as the predicted value. Since we are passing here, this one is the predicted data, and thereafter I'm also going to plot here the value for the actual data. All right, so I'm just gonna copy it and then I'm gonna just paste it here. LSTAT, median value, type, etc. will be same here, but in the data I'm gonna put here the test data. And if you notice, there we have the test data. All right, this one is the test data. All right, so there we have the test data as well. Let's go ahead and do it here on our data set there. I think that this test data is wrong here. We are getting the whole data set as a 506. This should not have came here. This should not have came here like 506. So we need to go back and visit where we did our data split. Perhaps we did something wrong here. I'm really sorry for this one. Yes, so this is split equal to true. This should not be like that. This should be split equal to true and split equal to false. Otherwise it won't be correct here. All right, because as of now, if you check there the dimension of the trained data set, there you will notice the 506, and similarly if you check the dimension for the test data set, it is also 506. So now if you run it once again, then we will get the correct data. Now we are getting the dimension for here. It's a 398, and now we are getting 108 value for the test data set. Let's go ahead and retrain it once again. Now we are getting here. This one is the standard error, which is MSE for the test data on the trained data set, which is the 5.98. And we already have metrics, and there we get this one on the test data set, which is 7.02 on the test data set. Let's go ahead and come back here once again. Now if you run it here, the test data set, we will get here only 108 values. All right, so there we have 108 values. Let's go ahead and just plot it here. We already have the data and we are going to plot it here. So once we plot it here, we get it like the line mode. Something is wrong here. Perhaps here this one. I need to just remove this line mode from there. All right, so instead of removing that line mode from there, I should put here this markers. All right, perfect. This is superb. So there you have, this one is the predicted value. So these dots are actually, dots are actual values. All right, so these dots are actual values here in the LSTAT, and this one, this number, if you notice, this line is actually the predicted value. So if you put your data, actual data there, and this one is the predicted value by our model here. One thing, if you notice there, this one is the not linear relation there. A non-linear relation is being shown here. It's like if line fits something like this, then you will notice that there will be decrement in a error. So for that, what we can do there, we have to refit our model with the non-linear, or you can say the polynomial regression. And for that, we are going to just copy our previous code from here. I'm just going to copy it from there In fact, this whole thing I'm gonna just copy it. So what you need to do here, select it from here, and then press your shift key in your keyboard and keep it as press there, and then click on here. Then you will notice these whole number of rows are selected. Then press C key in your keyboard, that is the copy. So these cells are copied there. Thereafter we are going to paste it here. Just press V in your keyboard, and here I'm going to simply say that polynomial regression. So this one is going to be a polynomial regression. There at the place of this LSTAT, we are also going to add here the square of LSTAT. So there you say the LSTAT. Alright, so it's like it's adding their LSTAT plus a square of LSTAT variable. So in this way, a nonlinear relationship is built for LSTAT. Let's go ahead and train it. Once you train it and run it, now you will notice a residual error are just 5.39. Earlier it was around somewhere 6 or 5.87 perhaps. Now it's 5.4 almost. Let's go ahead, and these metrics are actually already installed. Just try to get it on the test data set, and on the test data set now we are getting here the error, which is actually RMSE is just 6 there. So certainly our model is actually improved here. Let's go ahead and once again copy these two cells, and then we are going to paste it here. So once again we are going to predict it. Now if you notice there, we have just predicted for a 30. Now we are going to predict it for a 35 so that we can cover all these as well. So there we have here for a 35. Let's go ahead and predict it on new data and just plot it once again. Now we should see here a non-linear relationship. Do you notice there a non-linear relationship? And suddenly we have also seen there our RMSE score has decreased. Now you may also think that why not to fit here a third polynomial. Alright, so we can just copy it and paste it here once again, and thereafter we are going to put here the third polynomial as well. So instead of this second polynomial, if we put here this third polynomial, and thereafter you will notice the error is here 5.449, which is more than what we had earlier. So we are going to put it back once again as square 2, and then we are going to do here like this LSTAT and then the cube of 3. Let's go ahead and just run it once again. There once again you will notice we have now a smaller error, which is 5.3. At the second order polynomial we had a 5.4, but now we have 5.3, and this one has been also reduced to 5.75. Let's go ahead and then run it here once again. Now you will notice here the third polynomial is fitted here, and we have also reduced here. But if you try to increase your polynomial, later on you will notice that there will be a larger error there. So it's not like that you can increase your polynomial to infinite the number of order. There has to be some limit there. Let's go ahead and try to get the summary of your model. Once you type there the summary model, you will get here. So we are fitting here this formula. The value, the input features are LSTAT plus a square of LSTAT plus cube of LSTAT, and the data is trained data set. And if you notice there, the p-value still we are getting here 2.2 into 10 power minus 16. That's mean the less than that. Adjusted R square is increased to 65, and normal R square has been also increased to 65 there. All right, perfect. So this one is actually on the training data set. So this the summary model is available for the training data set there. All right, let's go ahead and try to plot our model. So if you plot here model, you will notice so many plots will be plotted here. So let's go ahead and try to understand what are these plots. The first plot is actually a plot of residual versus a fitted plot. There is a little non-linearity is there. So it says that there is also a fair chance that we can also improve our model. When you get here a complete straight line, then you have a perfect fit for your model. This normal QQ says that we do not have a normally distributed data. So if there is a straight line here, then it says that we have normally distributed data. So there is we don't have a normally distributed data because LSTAT is a little skewed. LSTAT is a little skewed there. All right, that means there is not a normal distribution if we plot the LSTAT there. Thereafter, you have this scale location and the standardized residual. So these are the standardized residual. That means this one is standard error. And this also says that for the various input, that's mean for various number of LSTAT, this standard error is also varying there. So the error is also not uniformly distributed to all LSTAT. So these plots says that there is non-linear relationship between the input feature and the target feature. And similarly, you see there the residual versus leverage graph there. Also there is the non-linear relation, and this one is the standardized residual. If you get there a straight line and these distribution, if there is something like normal distribution, in that case, you will notice that your model is perfectly fitting there. That's when you have a best model. That is difficult to achieve, but still as much as you can make this as a simple line, that's mean as a straight line, it would be really helpful, and in that case your model will perform better. All right, so in the next lesson we are going to look and we are going to analyze the multiple variable regression model. All right, now let's go ahead and implement here a multiple variable regression model. So the multiple variable regression model is also similar to our simple linear model, but only the difference is that we are going to include here a multiple inputs together. So for that, we are just going to copy this whole thing from there to here. So what will happen here? I'm just going to put it here. All right, superb. So there you have the model. I've just copied and pasted it here. So there you have a model equal to the LM medium value and then the LSTAT I. All right. If you don't know how to copy, you only need to do like this one. Select it outside and then press a shift key in your keyboard and then click on any of these cells. Then you will notice that these are highlighted. That means these are selected, and then press C in your keyboard. Then it is copied, and wherever you want to paste it there, select there a cell and just press V key in your keyboard. Then you will notice that it will be pasted there. All right, so there you have LM, median house price value, and these things we have already seen there. I'm just going to add here one more variable. Now there are two variables. So this one is mix of polynomial plus multiple variable regression model. All right, so I have just here added RM, and let's go ahead and just run it once again. Now you will notice the residual standard error is here now 4.77. All right, and earlier if you don't add RM, then you have this one as a 5.3. That means this RM is increasing. All right, so this RM is increasing our model accuracy, or you can see it is decreasing our MSE there. So it's still increasing your MSE. Let's go ahead and try to add some other variables as well. So you have RM. Let's go ahead and add here a crime as well. So if you add here a crime, then you have here 4.66. That means our model is increasing. That means R square is also increasing there. Now we have reached R square to 73. All right. Let's go ahead and try to add here another variable as well. Now I'm gonna add here index variable. All right, so there you have this index variable. In the index variable, now we are increasing actually. So our R standard error, our MSE is actually increasing there. So I'm just gonna remove this index there. Thereafter, I'm gonna add here the age of house. Then we notice there 4.55. That's mean it's still improving there. And after this age, I'm also gonna include here this age plus distance variable. All right, so there we have got 4.46. I don't see much of the difference there with the distance. If we include here the radius as well, we see just a little difference there. So if you keep adding these variable, it's not improving much there. So we can say that it's like we have reached there the saturation point there. 4.38 there. If we add the tax value there, and apart from that, if we add here the PT ratio, let's see what happened there. If we add there the PT ratio, sorry, that's the reason I said there, the PT ratio, so they are 4.12. That's mean we have drastically increased our model accuracy, and I think the R square is almost reaching to 0.8. And the final one I'm gonna add, and I'm gonna just try it. If we add here the black column as well, so there we get here the 4.059. So just a little improvement. All right, so let's go ahead and try to see here what is the MSE. So on the test data set, we are getting MSE of just 5.5. And on the training data set, we are getting the MSE of 4.0. Let's go ahead and try to see how these plots are changing there. But one more thing you need to understand there, we need to actually include so many. We need to include here many plots there. So that's going to be a difficult process. So what I'm gonna say here, I think it's actually not possible to plot the scatter plot for all the variable. So we have to plot a separate plots there for a single variable. So for all the plots, we cannot plot. So I'm just gonna delete this line and this line. So I'm just gonna see the summary. So the summary says that here we have a formula. That's mean this method we used to calculate, we used this method to train our linear regression model. Thereafter, we have these coefficients for these input feature. So if you have here, moreover, we say there high coefficient for RM. If there is a high coefficient for some variable, that's mean that particular variable is important there. And if you notice the black, by adding this black, we did not see much of the differences in the target output. So the coefficient of this is almost 0.01. But here for the third, the LSTAT cube, it's almost 0. So we did not see the much of the differences if we remove this LSTAT cube variable and LSTAT square variable as well. So the most important variable is RM there, and then the second most important variable is LSTAT. Thereafter we have other variables like distance also and the PT ratios. The higher coefficient means these variables are important. And moreover, you can also verify that with the p-value. So if p-value is less than 0.005, p-value is less than 0.05 only then that particular variable is important. So this LSTAT cube is having a value greater than 0.05. So this one is not important. We can discard this variable. We can also discard this age variable as well, since the p-value is also quite high. So we are going to remove age and the third cube of LSTAT variable. So this age is not important now, and the third cube of this LSTAT variable is also not important. Let's go ahead and run it. Now you notice there we have 4.05, and we are just going to see here if this model increases. So the model accuracy does not increase. Let's go ahead and there you have almost it's almost same. All right, there if you see there, it has just RMSE has just increased by a smaller factor, but in that case we once again calculate the p-value there. Now we see there all of these variables are most important variable. But you might be wondering that if p-value shows that the correct relationship of the important feature, then why our MSE increased a little? It is happening because the feature selection is not a simple task. This is a very complicated task. So what happened? P-values are calculated on only a single feature, and it does not take the influence of other feature. So when it calculates the age, for example, let's say when it calculates the p-value for age variable, then in that case it does not take the influence of other variables. But there could be a possibility that age variable is performing better with in the combination of the other variables. So the p-value alone cannot say that whether we can discard a particular variable or not. The p-value is only a preliminary information that a particular variable is important or not important. Let's go ahead and try to plot this model. So I'm just going to plot this model, and it says that there once again we have a non-linear line. It says that we have a non-linear relationship between input and the target output, and still we see there it's not linearly. So it's not linear there. That's mean the data is not normally distributed. So a normal distributed data, if there, then you might get this residual as a straight line, this one as a straight line, and there you will also get there a straight line. All right. So there you are also not getting a normal distribution, but moreover we can say that this line is a little straighter what we had seen earlier. All right. So the moreover, when we try to fit with the multiple variable regression model with the touch of non-linear relationship, then we get the better accuracy. If I say the better accuracy, that's mean higher R square score and adjusted R square score. And if there is higher adjusted R square score, that's when there is low MSE. Low MSE means there is low error in your model prediction. All right. So this is all about in this lesson. Thanks a lot for watching it. I'll see you next lesson.